So my name is Jake White and my supervisor is Sylvia Jangsha, and my project is a small cell-based solution for indoor navigation. So what is the problem? The problem is localization in an indoor environment and navigation of in an indoor environment. This would be, for example, an underground or an airport possibly, or a hospital. So why is this a problem? Satellite or GPS can't reach some indoor subterranean areas. This can be because there's on the ground and this can't reach, the signal can't reach, or the signal is too weak and will give a bad reading and a bad location. Indoor layers also can be quite difficult to navigate due to being repetitive, unintuitive, or just too complex, making it easy to get lost because of how maze-like they are if you're unfamiliar with them. So my aim is to create a low complexity indoor localization system that can work consistently and quickly. And my objectives are to implement an algorithm that can locate a user based on distances to certain reference points, use a model that can obtain distances to a user based on a property of wireless technology, such as the speed of light, and implement an algorithm that can navigate an indoor environment. So my solution for localization is trilateration. This uses the idea that there are three nodes that know the distance to the target, for example, a person's phone, and but the direction to the target is unknown. So this can be viewed as a problem with circles, and where where the phone is on the circumference of the circle. If you have two circles, then where they intersect will give you 2 points, and the actual location can be determined by using the third circle to rule out this one of the 2 points. This has some measurement errors when done in practice because you won't always get an exact measurement, and that can lead to some issues in giving you the wrong location. So how I get the intersection of two circles, I start off with two circles randomly placed on a 2D plane. And this problem is too difficult to solve, so I simplify it by putting the two circles on on a single axis, and that's easier to solve. And then I can use unit vectors to sub in, and this allows me to translate and rotate the problem to the original position, and I get these equations out of it. So how do I get the distance for trilateration? I'm using a path loss model. I'm doing this by using the PyLTE library, which allows me to input coordinates for the base station. This would be the phone, and then the coordinates for the end users, which are the receivers, the reference points I was mentioning earlier. And this will give me out the SINO and OSSI values, which are the signal to interference and noise ratio, and the received signal strength and intensity. Then I can use the path loss model to convert the OSSI value back into distance. And these will give me my distances, as I said earlier. So for navigation, this uses the idea that the signal attenuates as it travels. So for navigation, I'm using graph theory. And so how I do this is I take a map of an indoor location, and I would split it up into a grid of nodes. And then any walls that would be in the map will break any connections between nodes so that you can't travel through the wall because there's no connection there anymore. And then for solving these graphs, I was now my options down to two algorithms, Dijkstra's algorithm and A star. Both give me the shortest distance, but A star adds a heuristic for generally a faster runtime by making the search go in the general direction towards the goal. So here's a map I have for an example. I want to get to the end, which is the red square. And if I start at the green square at the top, I can run either of the algorithms and it will give me a route. But then if I want to start at this second square here in the middle, I will need to run the algorithm again. And again, if I have 100 algorithms, 100 people, I need to run the algorithm 100 times. This is repetitive and can waste time. So my solution is to start from the end and walk backwards. And this will give me the shortest path to every location in the map that's reachable. And then I can simply reverse the direction of each route. And this will give me the shortest route from any position to the end. And this is all done by running the algorithm once for the entire map, but it's only once, which is much faster than 100 times. And this means that since I'm solving the entire map, it's better to use Dijkstra because A star would be slower because of that extra heuristic, which is another thing to calculate. So one thing you will notice is in the bottom left, the green tile takes a quite unnatural route where it goes down, across, and down again. And it could just take a more direct route of just going diagonally from the start to the end. And to solve this, I'm using vector field path following. And I can use this because I have the distance calculated for our nodes in the map. And then I can make vectors using these nodes to give a direction that points towards the general location of the goal, the end I want to go to. I can add weighting to keep the vectors pointing away from walls so that I don't accidentally tell someone to walk into a wall. And this can be viewed here at the bottom of this obstacle, where where it points away from the wall, and then we'll get on a route that gradually goes towards the goal. So my work so far, I have basic simulation. I've implemented Dijkstra's algorithm. I've implemented vector field path following, and I have a robot that's able to navigate, a simulated robot that's able to navigate to the goal by following the vector field. I also have an algorithm that locates the robot via trilateration and a path loss model to get the distances for trilateration. As you can see in this image here, this is a simulation of a route I made. So I started the robot at the bottom of this obstacle, and it went down, around, and slowly back up, and ended at the goal. You can see it moved to the left to avoid this wall I added, and the pink dots are the measured locations from using the trilateration algorithm. As you can also see, the points are sometimes quite off from the actual location of the route and the actual location of the robot. And that's something I want to fix in the next coming weeks. So my plan for the future is to improve the accuracy of the path loss model and trilateration, and then improve the efficiency of the navigation algorithms. And then once I have them to a good enough level, I want to be able to navigate by using the measured location from trilateration instead of using the actual location of the robot, which I'm currently doing. And then I want to make a more complex map to represent a more complex indoor building. And I want to test that and make it work. And then eventually I need to do the report, portfolio submission, interviews, and assessment. My success criteria is to have a trilateration algorithm that can locate a small cell to within a reasonable amount of error in the simulation. The path loss model for indoors can work in a complex indoor environment and provide a usable signal. And the navigation algorithm is fast and able to give a valid route to quickly navigate a complex indoor area without error. And that's it. Thanks for watching.